the School Television Service presents Working with Science, an experiment in team teaching for grade 6 with Mr. Science, Stephen Fischer.
No, we're not going to bake a cake. There's a spatula, but we'll use the spatula in this case to represent vibrations. See, we're going to talk about sound today and how sound is transmitted. But before we talk about how it's transmitted, let's see approximately what sound is. Sound is the result of vibrations. Anytime anything moves up and down in a regular way, we can say it's vibrating. And in many cases, a sound will be produced by this vibration. This is a vibration. Now, this may not be vibrating fast enough to produce a sound, but we can use something like a tuning fork, which will vibrate fast enough and produce a sound. Here you can see the tuning fork moving, and possibly you'll be able to hear the sound. Now, to show the force at which this tuning fork is moving, I can take it and strike it, put it near this ping pong ball, which has been suspended on a string. Let's see what happens there. It's almost like automatic handball. Each time this tuning fork vibrates, it hits the ball and drives the ball a little further away. So tuning forks, through vibrations, produce sounds, and lots of other things produce sounds. Many of these sound-producing instruments, if we want to call them that, are very common, very ordinary things which we've been growing up with, like sound produced by tapping. What's vibrating? The skin head on this tambourine and these little metal discs, producing sound by tapping, or even by blowing across the top of this tube, causing the air within the tube to vibrate up and down, and we produce sound. Train leaving in 5 minutes. Here we're producing sound by vibrating air. Here we can produce sound by plucking, and what I've done in this case with this little instrument, I've tightened it so that we have bent the instrument up, just so the strings are more visible. But here I'll produce a sound by plucking. Rubber bands work the same way. So we produce sounds by tapping, blowing, plucking, or even shaking. What's vibrating here? Well, the beads within the maracas are bouncing around, hitting the sides, causing the side of the maracas to vibrate. So we have produced sounds. Now that we've produced sounds by ways of vibrations, how do we transmit sound? Or what carries sound? Sound actually has to be carried. Well, let's try the things that are around us. The thing around us most commonly is air. And here I have a jar full of air plus electric bell inside. This bell will ring when I close a switch. I'll close the switch and you'll hear the bell ring. Now when I open the switch, the bell stops ringing. Now what I'm going to do is this. I have attached to this jar a special kind of pump called a vacuum pump. There's a pump that sucks air out of things. It isn't the kind that pushes air into things. In fact, if you hook this pump up to your bicycle tire, you'd flatten them very flat. It would take all the air out of the bicycle tire. Now, I will start this pump going. This pump operates electrically. And as this needle right here goes around this way, see, ends up on the other side, it will be sucking air out of the jar. Now, we can't suck all the air out of the jar, but we can suck a great deal of the air out of the jar. Now, the bell will be ringing as I suck the air out of the jar. Unfortunately, this pump makes a lot of noise, so we can't really hear the difference between the sound of the bell when the air is removed from the jar while the pump is going. What I'll do is this. I will suck the air out of the jar. You'll know that the air has been taken out, or most of it's been taken out, by this indicator, this dial. Now, when we see that most of the air is taken out of the jar, I will shut off this hose by use of this little clamp. Remove the hose from the pump. This little clamp will shut off the hose. I will remove the hose from the pump and allow the air to go back into the jar very slowly. When that happens, we'll see if we hear a difference from the ringing bell when there is no air or very little air in the jar, and then when the jar has been allowed to fill up with air. First, let's start the pump going. Turn on the switch, and we are now drawing the air out of the pump, out of the jar. Now, I'll have the bell ringing. I've put the switch on, and the bell is ringing. Now, the bell is ringing, the pump is going. You may not hear the bell because of the noise of the pump. Well, let's take a look. You notice how far down that indicator has traveled, showing that we have removed a large percentage of the air from that jar. This pump is not big enough to remove all the air from the jar, but it can remove a great deal of it. Now, the indicator shows that most of the air has been removed from this jar. And at this point, I'm going to attach the clamp. To make sure, I'll pinch the hose and remove it from the pump. Now, we'll shut off the pump. Move the pump out of the way, and let's see if we can hear anything coming from the jar. Let's all be quiet now. Now, I'm going to remove the clamp and then allow the hose to become untwisted in my hand. Now, as I let the hose go, the air will come back into the jar. Let's see if we can hear a difference. Everybody listen. And you could hear that air suck right into the hose, sound almost like a whistle. Now the air has gone into the hose, into the jar, and I think we all pretty well could hear that the bell is ringing. Shut the bell off and see what we realize from this. We realize that air transmits sound. Without air, we don't get any sound traveling. So air transmits sound. That's a gas, or a mixture of gases. How about a liquid? Will that transmit sound? Well, let's try and find out. Here's a liquid, water. Fish tank, into which I have suspended 2 plumb bobs. Now, these plumb bobs are used by surveyors and engineers to mark a certain point on the ground. But when they tap together, they make a definite sound. When they tap together in the water, the sound will be slightly muffled because the water will change the sound as it's a little thicker than air. But will the sound travel through the water to something in the water? Now, I can't very well get into this tank and listen, but I can put a microphone into the tank. Now, I have taken a microphone and wrapped it very securely with plastic bags. We don't want any water to get at this microphone. It'll ruin the microphone. But I can suspend the microphone in the tank. Just get it to hold there. Now, I will tap these plumb bobs together under water. Let's see if the sound travels through the water to the microphone. Everybody quiet? Hear that? We have seen that sound, or heard at least, sound will also travel through a liquid. Sound will be carried or travel through gases. Sound also will travel through liquids. What's left? Come on, you know all about these things, states of matter. Gases, liquids, and solids. Here's a solid, very solid. It's a steel bar. This steel bar is resting on an alarm clock. Now let's see what we can do to see if sound travels through a solid. The alarm clock is ticking. Now, if sounds travel through a solid, the ticking noise or the vibration should be carried by this steel bar right up to this microphone. Now, if that is the case, we should be able to hear the ticking through the microphone. But to make sure that we're hearing the ticking through this microphone, I will, by means of this string, lift the microphone, or lift the bar, off the microphone. At this point, if the sound is being carried through the bar, the ticking should stop. If the sound is being carried through the air better than through the steel bar, we'll still hear the ticking from the clock right through the air. Let's see first if the sound is traveling through the bar, and also if it travels through the bar better than through the air. Now let's all be quiet again and listen. Let's see if we hear the ticking. I'll listen too. Hear it? Now, listen. Hear it now? Now, you did hear a definite ticking noise through the bar, and when I did lift it, the ticking stopped. Now, we see two things. First, that sound will travel or be carried by a solid right up to the microphone. Also, I think we can assume by this steel bar that in this case, the bar or the solid is a better conductor of sound than the air between the clock and the microphone. See? Otherwise, when I took the bar off the clock, you would still hear the clock because of the air between the microphone. The air is not as good a conductor of sound as the solid bar. In fact, the Indians used to put their ear to the ground, and actually they could hear the vibration of horses' hooves many, hundreds of feet, maybe miles in the distance. This vibration would be carried through the ground, and the Indians could hear it. This is where we get the expression, keeping one's ear to the ground. So early communication was carried on right through the Earth's surface. Now, we've seen that sound is carried by gases, liquids, and solids. We are using various methods of conducting sound right now. But one of the ways that my sound is reaching you is through the conduction of sound through air. I can talk to you right through this microphone. But I'm not talking directly through the microphone. Air is carrying that sound. Now, another way that air carries sound is through this form of microphone. It's not an electronic type, but it's a sound carrier. You know, your doctor has used this many times, giving you your regular physical checkup. On the end of this stethoscope, we have a disc. And this disc has a very thin face, a face which will vibrate in and out very easily. Now, this face is attached, we can remove it, to a tube, which is filled with air. Now, you see the back of the face is just open. There's an opening there, and there's air in there. This tube also is filled with air. The sound vibration will travel from the disc through the air within the disc to the air within the tube. And then this sound will travel through the, or be carried by the air, through the air in the tube until it gets up to this sort of fork in the road. Now, both sides are filled with air. So this sound will travel right up through both sides, or be transferred, carried through both sides, right up to these ends, which are in the doctor's ear. And he can hear very minute sounds like the beating of your heart. Now, we're not going to listen to my heart, at least not in this program right now, maybe sometime in the future. But let's see if we can hear through a stethoscope. I'll put the end back on the stethoscope and place the earpieces on our microphone. I'll hold them right on here and make believe that this represents our ears. Then I will tap very gently on the end of the stethoscope. Let's see if we can hear any noise through our stethoscope. See if the stethoscope really works, what the doctor's just doing. Now, listen quietly. Hear that sound? That's a very minute sound. I was tapping very lightly, but that sound was carried through the air, in the stethoscope, through the solid end, through the air, right up to the doctor's ears. How about my voice? Even though I'm using a microphone, air is working to carry sound. I've set up an additional microphone right here. Now, in this demonstration, I will block off sound from this microphone, but you will still hear me because the air that I'm causing to vibrate will go down to this microphone. But you will see that when I block air, the sound tends or seems to stop. Now, as I speak into this microphone, I have attached a meter to the other side of this amplifier. It's actually a tape recorder that I'm using as an amplifier. Now, as I speak, the meter right over here will correspond to my voice. No speaking, no movement of the meter. High speaking, high movement of the meter. Now, let's stop for a moment and introduce the card. I have a large card here which will block off most of the air. And let's see if there's any change in the meter when I block the air from my mouth to the microphone. Here we go. I'll block it off now. And let's look very carefully at the meter and see if there's any change. Now you notice you still hear me because my regular microphone still picks up my voice. But the meter doesn't react too much because I am blocking the air away from the meter by blocking the air between the microphone and my mouth. When I remove this card, we find that the air tends to go directly from my mouth to the microphone, and then you can see there is a definite reaction. So we see that this air is necessary for carrying of speech. How about a place where there's no air? Where's that? What do you tell me? Where is it? Up on the moon, right. As far as we know, there's no air up on the moon. And how is our astronaut going to communicate with a fellow astronaut? He can't speak into a microphone like this directly, but he can hold the microphone against his voice box or larynx, and this is a vibrator. You will hear me as I place this microphone against my larynx or voice box through direct transmission, vibration of the larynx directly to the microphone. It will sound different because this microphone is not made for that type of transmission. I will say, you are now watching Working with Science, without the aid of air right now. Listen. You are now watching Working with Science, on the phone with aid control. That sound transmission, meaning the sound from our mouths to our microphones. See, it did sound differently. So sound travels through lots of things. That's only half of the story. The other half of the story is hearing it. And if you look at this diagram, you'll get a sneak preview of something that we're going to go to next week, and that is the study of the ear. Now, what have we learned? You tell me. Let's see if we can review all the material that we've covered today about transmission of sound. First thing we have learned about the transmission of sound is, now, think deeply. First thing, sounds are made by vibrating objects. We tapped and we plucked and made all sorts of different noises. Also, sound or sounds travel through solids, liquids, and gases. And we did all those demonstrations right here in our class. Next time we're going to learn about how we hear and also how animals hear. See if they use the same process as we do. Until then, bye.
You have been watching Working with Science, a presentation of the school television service of Channel 13, WNDT, prepared and broadcast by Stephen Fischer. This series is produced in cooperation with the Bureau of Science, New York City Board of Education.